And welcome back. As we continue our cosmic journey, we have been having a good discussion about how exoplanets play a role in planetary systems, but let's go ahead and include some new information that we have that could give us insights into the perspectives we have on planet formation. So let's start off first by examining the hot Jupiters that we've talked about, because these of course have been planets that we have found that are pretty massive, forming near their host star. The traditional model for the formation of planets really kind of only works if the giant planets are formed far enough away from our central star, about 5 to 10 AU, where the disk is actually cold enough to have a high density of solid matter needed to make the planet cores. It cannot explain the hot Jupiters, though, which again are located very close to stars where we don't have solid matter, because at this point it would all be completely vaporized. It also cannot explain the elliptical orbits we observe for some exoplanets, because the orbit of a protoplanet, whatever its initial shape, will quickly become circular through interactions with the surrounding disk of material and remain that way as the planet grows by sweeping up additional matter. So what we need ultimately is a new model for forming planets close to the searing heat of the parent star, or a way to change the orbits of the planets originally formed in colder regions that are far from their parent stars so that they can travel inward after they form. Now, most of our current research supports the second option. There are two ways that giant planets could travel inward. Calculations show us that if a planet forms while a substantial amount of gas remains in the disk, then some of the planet's orbital angular momentum can actually be transferred into the disk. As it loses momentum through a process that reminds us of the effects of friction here on our own planet, we're going to notice that the planet tends to spiral inward. This process can actually transport giant planets initially formed in cold regions of the disk closer to the central star, thereby producing the hot Jupiters. Now, gravitational interactions between planets in the chaotic early solar system can also cause a newly formed giant planet to change its orbit to be much more elliptical, therefore carrying it into the hotter regions closer to the star. Now, once it is in that more crowded region, the same forces can then cause its orbit to become much more circular again, but in the hotter region that is again closer to the star. Now, in some of the cases that we are examining, we can actually use the combination of transit plus the Doppler measurements to actually determine whether the planets orbit in the same plane and in the same direction as the star. For our first few cases, things seem to work just as we anticipated. Much like our own solar system, the gas giants orbit in their star's equatorial plane and in the same direction as the spinning star. But then we got some startling discoveries made of these gas giants. They were orbiting at right angles or even in the opposite sense as the spin of the star. So how could this be happening? What was causing this kind of unusual behavior? Again, what we think is there must have been interactions at some point between the planets, either due to a passing star or there was another planet that perturbed the orbit. And so this is, of course, a very good conversation to have when we look at how we are forming planetary systems. When our own Milky Way galaxy was young, the stars that formed did not contain many heavy elements such as iron. We actually needed several generations of star formation and star death that were required to actually enrich the interstellar medium for subsequent generations of stars. Now, since planets seem to form kind of from the inside out, the heavier materials, of course, are going to settle through differentiation, starting with the accretion materials that can actually make up rocky cores from where our planets start. Astronomers wondered when in the history of the galaxy planet formation began. So if we look at the star Kepler 444, we can see it has a tightly packed system of about 5 planets. The smallest planet is comparable in size to Mercury, and the largest much more similar in size to Venus. Now, all 5 planets were detected as they transited their parent star. All 5 planets orbit their host star in less the time it takes Mercury to complete one orbit around the Sun. Remarkably, the host star Kepler 444 is more than 11 billion years old and formed when the Milky Way was only a mere 2 billion years old. So the heavier elements needed to make rocky planets must have already been available at that point. And this ancient planetary system actually sets the clock on the beginning of rocky planet formation to be relatively soon after the formation of our own galaxy. Now, the Kepler data that we have demonstrates that while rocky planets inside Mercury's orbit are missing from within our own solar system, they are actually common around other stars, like we saw with Kepler 444. When the first systems were packed with close and rocky planets discovered, we wondered, why are they so different from what we see within our own solar system? When many such systems began to be discovered, we actually began to wonder not about why are things different, but what if our solar system was the thing that was different? This actually led to some speculation that additional rocky planets might have once existed close to the Sun within our own solar system. Now, there is some evidence from the motions in the outer solar system that even Jupiter might have once migrated inward long ago. If this postulation is correct, then the gravitational predations of Jupiter could have actually dislodged the orbits of the close-in rocky planets, causing them to fall into the Sun. Now, consistent with this picture, astronomers now think that Uranus and Neptune actually probably did not form at their present distances from the Sun, but rather were actually a lot closer and actually resided where Jupiter and Saturn are now. The reason for this idea is that the density in the disk of matter surrounding the Sun at the time the planets was formed in was actually so low outside the orbit of Saturn that it would take several billion years to actually build up Uranus and Neptune. Therefore, scientists have developed computer models demonstrating that Uranus and Neptune could have formed near the current locations of Jupiter and Saturn, and then have been kicked out to larger distances through the gravitational interactions with their neighbors. Now, exoplanets have given rise to a new picture, therefore, of planetary system formation. One that is not so neat and ordered, but much more chaotic than we originally thought. And so that really kind of starts begging the question, well, how do we find habitable exoplanets? Well, thousands of exoplanets have been discovered in the past 2 decades. Every observational technique that we have has really kind of fallen short of finding more than a few candidates that actually resemble Earth. Astronomers are not exactly sure what properties would define us another Earth. For example, do we need to find a planet that is the same size and mass as Earth to really replicate the conditions? Because if we do, this actually can be very difficult, and it actually may not be as important as we think from the perspective of habitability. After all, we have no reason to think that life could not have arisen on Earth if our planet had been a little bit bigger or a little bit smaller. Like if we had a planet that was like 1.2 times bigger, yeah, we might have had a little bit more gravity, but our life could have probably still developed very similar to what we have today. So how habitable a planet is actually really depends on both its distance from the star and the nature of its atmosphere, such as having a greenhouse effect that can actually make some planets warmer, such as our own, as long as it doesn't get to the extreme point as we see on Venus where it runs away. So we can ask other questions too, to which we don't yet know the answer when we're looking at exoplanets. For example, does this twin of Earth need to orbit a solar type star, so a G-type class such as our own sun, or can we consider other candidates, such as the numerous exoplanets that orbit K and M class stars? We have actually a very special interest in finding planets that could support life much like ours, in which case we need to find the exoplanets that are within their star's habitable zone, where surface temperatures actually end up becoming fairly consistent with the possibility of liquid water on the surface. And this is probably the most important characteristic in defining an Earth analog exoplanet, looking for the presence of liquid water.